Okay, hello. So here's the next in the series on step maths questions. I won't say any details about what that means. You can check the other videos for some background knowledge. This is question 6 from the 1988 paper 3. So it's the same paper as the one I looked at in the last video. So won't say very much about this question. It's a bit unusual in that it's very short. So that means they're not giving you many hints, but on the other hand it might be quite a quick question, a fairly easy question to do if you get the idea of it quickly. So please do take the opportunity to pause the video, read the question and try to solve it, and then come back when you've given it your best shot. Alright, so I will now start doing my my answers. So interesting question because as I said, no hints really, just here's something, do something and show something. Yeah, so the structure is we have a particular function, sine 2x cos x. We need to find something which is the 1988th derivative of the function. So a bit unusual. Obviously the 1988 is a bit of a joke. This kind of joke is quite common in maths exams, using the year of the actual paper. So find this very high derivative of f, and then let's say we find that, then we've got to show something. We've got to basically find the x value for which this derivative, so it doesn't mean the derivative, it means the 1988th derivative is 0, and then we express what that value should be. And here they do give a bit of a hint because they tell you how to find that solution. Alright, so part 1. How do we find this derivative? Now it's definitely worth mentioning what the wrong approach is, because at the end of the day, if they don't give you hints in these questions, you are quite often going to go down wrong paths. You're going to go the wrong way sometimes, and you have to learn to deal with that. And part of dealing with that is realizing that sometimes when you choose, so the questions offer you a choice in many cases, and when you choose something that's not a good choice, you should develop the skill of recognizing that it's a bad choice by seeing that what's happening is not working. So what do I mean here? Now the wrong way would be to just take the normal way of differentiating the function f. If I differentiate the function f, I'm taking the derivative of sine 2x cos x, and I'm going to use which rule? How do we differentiate something like this? The answer is product rule. So it's derivative of sine 2x times cos x plus derivative of cos x times sine 2x. Okay, so that gives me some formula. It gives me 2 cos 2x sine x cos x. Sorry, what am I saying? 2 cos 2 cos 2x, which is the derivative using the chain rule of this function, times cos x minus sine x times sine 2x. Now of course that's the first derivative. So when I say wrong way, what way is this? You might think, well, don't be ridiculous, you can't just differentiate it once and then differentiate it 1900 times. No, of course I don't intend that, but one approach to a problem like this is a kind of a hope approach, which is that if you need to do something a large number of times, it might be the case that if you do it 2 or 3 times, you spot some simple pattern. For example, you might find that if you differentiate this 3 times, that you come back to the beginning or something, or a constant times the beginning. In other words, there might be some number n such that the nth derivative of f of x is maybe either equal to or proportional to f of x itself. See, if that were the case, then you would have a repeating pattern. And so actually when I started doing this question, that was my first thought. I thought, well, maybe there's some repeating pattern. But when I looked at this result here, I thought, oh dear, it looks a bit messy. See, I'm already starting to worry that maybe I'm going the wrong way, because now if I want to differentiate this again, the second derivative of f, I'm going to have to do the product rule twice. Unless somehow I rearrange this, that certainly might be possible, to rearrange this into another form. But if I don't rearrange it into another form, I'm going to have to apply the product rule twice. So product rule here gives me minus sine 2x times 2 times cos x plus cos 2x times minus sine x, and that's just the first part. Yeah, then I've got minus this thing here, so I've got minus cos x times sine 2x, and then the next term is plus 2 sine x cos x sine 2x. Sorry, what am I saying here? 2 sine... no, sorry. This last term would actually be sine... what have I done? Yeah, sine x times 2 times cos 2x. Okay. So at this point, we're really starting to feel like, oh, this doesn't feel right, yeah? If I start doing it again, you know, I could tidy this up. I can tidy this up, and I'll get something that, you know, it's always going to be the same basic structure. Like, for example, the cos 2x and the cos 2x here are linked, but then there's this factor 2, so you're usually going to end up with two terms, and then you have to apply the product rule, and it's all a big mess. So this was the point at which I started to think, don't like this method. Maybe it works, maybe it's possible with some cleverness, but I'm thinking to myself, this is probably not what the examiner intended. So let's put all of this in a sort of separate box and say, okay, here it is. This is my first effort. Don't feel very comfortable with it. So then you think to yourself, well, maybe there's another way. Now you should know quite a lot about trigonometry, and you know there's all kinds of formulas that can be used. You know, cos 2x is cos squared x minus sine squared x, for example, or obviously sine 2x is 2 sine x cos x, and so on and so on. And you might know a lot of different formulas. But is there a formula that might change the structure of this so that differentiating it becomes easier? And really, I can't give you any more of a hint than that. You want to change the structure of this, find another way to write this. Now, you might be thinking, sine 2x is 2 sine x cos x, so sine 2x cos x is 2 sine x cos x times cos x, that's cos squared x. And, you know, maybe it's even worth writing that as 2 sine x minus 2 sine cubed x. Maybe that would work. I don't deny it. But actually, by far the best idea, in my opinion, is to rewrite this using the idea of sine A cos B. Now, this is a very useful trick in many situations, so if you haven't learned it, please pay attention and learn it now. The trick is that this can always be written, so let's say this is a product. This can always be rewritten as a sum or a difference. Now, what do I mean by that? Well, it's based, if you don't remember the formula, it's based on an idea from the compound angle formula. So sine A plus B is sine A cos B plus cos A sine B. Now, that much I certainly expect that you do remember. And sine A minus B, by the same token, is sine A cos B minus cos A sine B. So in order to, so what this does is it takes a compound and converts it into, well, let's put it this way. Here we have products. That's a product. That's a product. And here we have a sum or a difference of angles, don't we? So what we can do is combine these two equations as if they're simultaneous equations. If we add 1 and 2 together, what do we get? We get sine A plus B plus sine A minus B equals 2 sine A cos B. So here we have a formula which serves the role of converting a product into a sum of two different angles. So therefore sine 2x cos x, so we can treat A as 2x and B as x. So therefore sine 2x cos x is equal, now we have a 2 here so we need a half, is equal to 1/2 of sine of A plus B, so that's sine of 3x, plus the sine of A minus B, that's the sine of 2x minus x, that's the sine of x. So now we see that rewriting f of x in this form is obviously a good idea. Again, it's not the only way, I'm sure. You can be a bit clever with your trigonometry in other ways, but this is a very good way to do the question, I think. So we have this rewritten form of fx. So we see that, for example, the first derivative of f of x is so a half of 3 cos 3x plus cos x. Now, the main thing you need to know about the derivatives of trig functions is what you might call the four-way periodicity, or the four-step periodicity. And the four-step periodicity, and that's not an official term, I just made it up, but is of course that if we differentiate once, we get cos, we differentiate twice, we get minus sine, we differentiate 3 times, we get minus cos, and we differentiate 4 times, and we get sine x. Okay, so very, very key knowledge, in my opinion, about trigonometry. This, that fourth derivatives of trig functions go back to the same trig function. So that means that if you asked yourself the question, what was the 178th derivative of sine x, do you see how you could work that out? Okay, so the 180th derivative of sine x, because 180 is a multiple of 4, would be sine x. So we're just going back twice along the list there, so we'll get minus sine x. Yeah. So it's basically this one here, because every 4, so 4, 8, 12, 16, 20, and so on. Each one of those derivatives is sine x, and so on. So maybe all of this is well known to you. I apologize if I'm boring people, but I know that some people won't know this. Now, from that knowledge, we can see that we've got almost exactly the same situation here. Yeah. So in the case of differentiating this function fx, we see that we have two terms, sine x, which will obey exactly this process, but then we have sine 3x, which is not quite the same, but it effectively is the same, you see, because the only difference with sine 3x is in each of these terms. Suppose I use another colour and I put a 3 here, I'm going to get a 3 here, and then 3 here, I will get 3 and then another 3 from each step of differentiation. Each step of differentiation we apply the chain rule, which means we take out a factor 3, and at the end we're going to get 3 to the 4 sine 3x. Yeah? So we get a power of 3 for every step of differentiation. So this logic tells us that the 1988th derivative of x will be exactly the same as, so here, sorry, I should be clear, fn denotes nth derivative. That notation is not completely standard, so you should probably define it. So the 1988th derivative, because 1988 is a multiple of 4, will be exactly the same as f of x, except for one detail, which is that we will get the 1988th power of 3 in front of the term sine 3x, and the sine x will be exactly the same for, again, the same reason. Okay, so this is the answer to the first part of the question, isn't it? Yep. So the first part of the question was, if I can just scroll up. the first part of the question was to find the 1988th derivative of f of x. Okay, so that was easy once you saw the easy way to do it, but it could, you can see from this kind of thing here, it could be a real nightmare if you get yourself into a mess. Now we're going to show that the smallest possible value up here, show the smallest possible positive value of x for which this derivative is 0 is, and they give you a formula, pi over 3 plus epsilon, where epsilon is approximately, obviously an important word, approximately equal to this number here. Okay, so what we're doing now is considering the zeros of this derivative. So considering the zeros of this derivative means we're going to set the 1988th derivative of f of x to 0, and that's half of 3 to the 1988 sine 3x plus sine x, all equal to 0. Okay. Now, suppose, now we're trying to find the smallest positive value of x. So suppose x is between 0 and pi over 3. Then the term 3 to the 1988 sine 3x is positive. Why is that? Because if x is less than pi over 3 and between 0 and pi over 3, then 0 is less than 3x is less than pi. So sine, as you know, looks like this between 0 and pi. So that means that in this region the value of sine 3x is positive. Now sine x, by the same token, is also positive in that region. Therefore, there does not exist, let me use a terminology there does not exist x in the interval 0 to pi over 3 such that 3 to the 1988 sine 3x plus sine x equals 0. Okay, so that was a preparatory step, just to show that because they give you a clue in the question in case it's not obvious. They tell you that we're looking for a number which is a bit more than pi over 3, and we're trying to solve the problem of the smallest positive value of x for which this derivative is 0. So from that you can see that they're suggesting that the answer we're looking for is more than pi over 3. So we need to justify why the number we're looking for is more than pi over 3, and this is our justification here. Okay, so we justified that x that we're looking for is bigger than pi over 3, but now we're being asked to more specifically find the approximately correct value for the first positive 0 of the derivative. This is the form it should take. So this step is in my opinion maybe less difficult than the first part of the question, because they tell us exactly what to do. They tell us to set x equal to pi over 3 plus epsilon. Oops, that's e, not epsilon. And so because we're finding an approximate answer, we're being given a big clue. Yeah. They're using the number epsilon because that usually refers to a small number, traditionally in maths. And also we're only finding the approximate answer, so the question becomes, how can we approximate? Yeah. So let's write down the 1988th derivative of f again. In exact form. But this time we're going to substitute x equal to pi over 3 plus epsilon. So we have the sine of 3x, which is 3 times x plus pi over 3, plus the sine of x, which is pi over 3. Oops, sorry, what did I... Sorry. we're substituting pi over 3 plus epsilon for x. So that should be pi over 3 plus epsilon. Now all of this should be equal to 0, and we're going to find epsilon. Now there's a tricky point of logic here. How to approximate? Excuse me, what I've just said is not is a non sequitur. The tricky point of logic we'll come to in a moment. First question is how to approximate. Yeah. So what kind of approximations do we know? In trigonometry, we know approximations for sine theta. Sine theta is about theta if theta is small and in radians. And we also know that cosine theta is about 1 for theta small in radians. Now we could put 1 minus theta squared over 2, but I can see from the question that there's going to be no square of epsilon here. That will be too complicated. Anyway, so that's a reasonable approximation, or that's the kind of approximation that we're allowed to use in these questions. So now what do I mean by a tricky point of logic? I mean we're solving this equation for epsilon. We're trying to find the value of epsilon. And what we're doing is, if we use an approximation, we're going to assume that epsilon is small. As I said here, this was a big clue. If epsilon is small, then the approximation is valid. So what we need to do is to assume that it's small, then find the formula for epsilon, and then verify that it is indeed small. It's a bit of a strange way to do things, but you could also argue that just from looking at the equation and thinking about its structure, that because of this very large number 3 to the 1988, that means this term is dominant, the left-hand side term is dominant, which means that the answer we're looking for must be very close to the 0 of sine 3x, and the 0 of sine 3x is pi over 3. Yeah, so that logic, that's good logic for kind of thinking about the problem, but maybe it's not good logic for constructing an answer. So what we need to do is use the compound angle formulas and then apply the approximations assuming epsilon is small. So first let's use the compound angle formulas here. We can ignore the 1/2, that's disappearing. So this means that 3 to the 1988, and now using sine of a plus b, I've got sine pi cos 3 epsilon plus cos pi sine 3 epsilon, and then I've got, so that's all included in the 3 to the 1988. Then I've got plus sine pi over 3 plus epsilon, that's sine pi over 3 cos epsilon plus cos pi over 3 sine epsilon is all equal to 0. Okay, now at this point we need to use the approximations, yeah? So assuming epsilon is small, we can write, so now we're going to switch over from an equation to an approximation, yeah? So using sine, so first of all let's write step by step. 3 to the 1988. Now sine pi is 0, so the first term is all 0. The second term has cos pi, so that's -1, and then it has sine 3 epsilon. So sine theta is about theta, so I'm going to write 3 epsilon. Okay. Now the next part is sine pi over 3 cos epsilon. Well, cos epsilon is about 1 if epsilon is small. So I've got sine pi over 3, that's sine 60, that's root 3 over 2. And the next term is cos pi over 3, that's 1/2. And then sine epsilon is about epsilon if epsilon is small. So this quantity is not equal to, but approximately equal to 0. Now let's rearrange it to find a formula for epsilon. So therefore, let's do this. We've got, let's factorize out epsilon. We have epsilon times minus 3 to the 1988 times 3. Then I've got plus 1/2 is approximately equal to minus root 3 over 2. Okay, so all we need to do now is rearrange. Yeah, there's more than one way to do this, but if we simply observe that because 3 to the 1989 is much bigger than 1/2, we can simplify this to epsilon. In other words, ignore this term. This term here can be ignored. There's more than one way to do that, but that's fine. So epsilon is approximately, now we have a minus sign cancelling on both sides, so I have root 3 divided by 2 times 3 to the power of 1989. And I believe, I hope, that is the same as the formula that we were given. There it is, root 3 over 2 times 3 to the minus 1989. So that was the required approximate formula for epsilon. So I'm just going to say a little note here. This is valid because epsilon is small. So clearly this is a small number. So because it is a small number, the assumption that we made is valid. So if the assumption we made is valid, then the logic is correct. Yeah. So that's the idea. So a slightly unusual question. Only 2 parts. Very little in the way of hints. And I think the main thing is just to, hunt around a bit, look for the easiest way by considering different forms of the same function. So I think I'll stop there. Hopefully that was helpful. So thank you very much.